Good afternoon, my name is Janesler Gonzalez. I'm here with my colleagues Jorge, Coria, and Sheffield, and together we are the 2016 FIU Formula SAE Powertrain and Body Team. Our advisor for this endeavor was Dr. Janesler. Formula SAE, or FSA for short, is an international engineering competition in which universities from all around the globe come together and compete in their open-wheel Formula-style race car. It's going to be taking place in Michigan on the following dates, May 10th to the 13th of next year. And thus far, there are 120 registered teams. These teams are from Canada, Mexico, the United States, Germany, Austria, and so forth. The FIU FSAE team is rather young, about 5 years, whereas the competition has been being held for about 40 years. And right now, there are about 20 to 25 active students. The organization's goal was to put the car together by December 2016. Our senior team goals, however, are to create the main components of the FSA vehicle in order to allow the organization to have time to integrate these parts. Team 1, which is us, corresponds to the powertrain, aerodynamics, and electricals.
Can we take a moment? It seems like we have an issue with PowerPoint. Is it okay if we update the folder to make sure that we're running on the current one? Thank you. Sorry, Mom.
We apologize.
Sorry, guys.
We're back. We're back online. So our tasks are segregated by the colored blocks. We are team 1 on the bottom with the blue blocks, taking care of the powertrain, aerodynamics, and electrical systems, whereas our partnering team was taking care of the chassis, suspension, and the like. Our particular team goals, which is developing a data acquisition system for the cooling system, also while redesigning it. As far as the aerodynamics go, because the chassis has to be renewed every 2 years, we have to also create a new body. And the goal was to make a new and improved aerodynamic package. While the electronics, as far as the electronics go, the ECU had to be calibrated to accommodate further changes. Our team goals directly impact the organization's goal, which is to place higher in the rankings. As you can see, design, fuel efficiency, endurance, these are all areas where we are impacting directly.
So one of the first things that we wanted to try to establish for the team was a data acquisition system that we can use to start an analysis on the engine with. This is information that the judges at competition are interested in, such as how much heat you're rejecting through your coolant or how much heat you're rejecting through your radiator. And so we put together the following system. It's essentially just a pair of thermocouples and an inline flow meter that we could put in the inlet and outlet ports of the engine block. And if you follow basic heat transfer principles such as measuring the flow rate, temperature differential, and knowing fluid properties, you can measure how much heat is being rejected to that fluid mass. We also use the system above to generate a pump performance curve for the engine. This is information that's going to be relevant to the team so long as they continue to use the same engine. And essentially, it'll make it so that if some type of engine heat rejection analysis needs to be done, all they would need to do now is monitor the temperature. If at some point the team decides to change engines, we can go back to the previous system and generate a new curve and facilitate the process. For the cooling system, we had a couple things to consider, such as FSA rules. For one, they mandate that we strictly use water. We also wanted to migrate from a single radiator to a dual radiator system for potential benefits, such as weight savings and packaging. And as far as sizing of the system, we had to consider 2 main states of the engine, the first being at idle, where most of the heat exchange is taking place in the radiator with a combination of the fan. And we had a coolant temperature limit range to be within 194 to 212 degrees Fahrenheit. And the second state, which is a dynamic state, when the car is running, the heat exchange is taking place between the radiator and the air around it. In this case, the temperature threshold increases to around 235, and this was pointed out to us by the Yamaha Service Center. Now, between the 2 states, idle is generally the more critical one. That's because, as we showed before, the pump performance is very low, and there's not a lot of airflow around the system, so the temperature on the engine tends to ramp up until it overheats. The second state, the more dynamic state, generally speaking, the car velocity does a good job at heating and cooling. So for the radiator selection, we wanted to try to use what was available in the market. But since there wasn't much available in the market, we decided to start with that instead and try to build the rest of the system around it. we used the previous Radiator as a reference, knowing that it was a little bit oversized, and tried to downscale it from there. There wasn't much available that was smaller, but with that in mind, we ended up selecting the Radiator CRF 150, which also happened to be on sale, which was beneficial to us, and it had a core area of around 72.5. This resulted in roughly 16% reduction in total core area, which we were looking to make up with the addition of thermal coating, as well as sizing of a proper fan. In aluminum weight, we saved around 4 pounds just from the size alone, and because we were transitioning into smaller fitting, we also saved a lot of weight in water, roughly around 1.3 pounds of weight per foot of hose, and generally we use around 6 feet of hose for our system, so that's an additional 8 pounds of weight that we were saving.
Now that the radiators have been selected, we need to figure out how we were going to configure these, the two possibilities being series or parallel. Through our independent research, we couldn't find sufficient information online to make a decision based just on that, so we take it upon ourselves to create a model scale of this and validate it ourselves. Through this model scale, we're also able to test different thermal coatings and find out which one is most beneficial for us. So our model scale testing apparatus can be shown in the image on the right. And now that we've set up our model's cooling system, we can now test the radiators in series versus parallel. What we found in doing so is that the radiators configured in series cooled the fluid at a rate of 6.4% faster from a common high point to a common low point. And not only did they cool the fluid faster, but they also had a greater temperature difference across the radiators of approximately 3.57 degrees. Also with this model scale radiator setup, we're also going to test the different thermal coatings. So we have 3 different thermal coatings that we're going to test from engine armor, those being TD, AB, and C3, and our baseline no coating. These designations are just generic names that were given just so that we remain impartial during our testing. Our testing found that the thermal coating TD provided us with the best increase in performance, an increase of approximately 20%, so we went ahead and chose that one. Once we've selected the configuration that we want for the radiators and the thermal coating that we're going to use, we move this on to the full scale testing. So on the engine stand, as you can see here, we went ahead and we built an air duct after the radiators just to find a data point so we can say at a certain airflow, at a certain ambient temperature, we're getting sufficient cooling. So that data point for us was 8.5 CFM at an ambient temperature of 75 degrees Fahrenheit. That showed us that at steady state we were getting engine temperatures of approximately 189 degrees Fahrenheit, so that was sufficient for us. With this, we were also able to calibrate the thermistors on the PD3, which is the tuning software for the engine. And now that we selected and got a data point on how much airflow we need, we can go ahead and select the fans for it. So a few of the fans that were surveyed can be shown tabulated on the left-hand side. The one that we ended up choosing was the QFR based on its performance, its power, and its cost. The performance here is just an estimate of our own based on the free flow airflow performance of the fan, coupled with considering that there's a pressure drop across the radiator. And sorry about that. That was a video that we have here. So this is just showing some of our testing that we had. We were able to validate that with these current fans and our duct system after the radiators, that we were able to produce 31.5 CFM, and that gave us a steady state temperature of 182 degrees Fahrenheit. So this is more than sufficient for us. Just as a reminder, the engine operating temperature is from approximately 190 to 230. So of course this system will not be going continuously. It's on a closed loop feedback system, so it'll be turning on and off. But this just tells us that it's more than suffices for our application. In summary, we were able to reduce the weight of the cooling system on the vehicle by approximately 12 pounds. We were able to find that the series was a greater configuration, and we went with that configuration. We chose the TD thermal coating, and also we were able to get some engine heat rejection data on the vehicle that both served us well for choosing and sizing the cooling system, as well as provide the team with information that will outlast us and benefit them. The total cost for this cooling system is approximately $350. That takes into account the parts that were purchased just outright, or at a discounted rate, or sponsors.
Thank you, Ryan. Now that the cooling system was concluded, we had to take a look at the aerodynamic package because, to reiterate, a new chassis had to be built, meaning a new body has to be built around it. And the goals for this were to seek an improvement from last year's model. Also, while staying within the FSA restrictions. The most importance were the dimensionless parameters, the coefficient of drag and coefficient of lift, since this is not a structural part. And to get those values, we had to subject the CAD to a CFD analysis on ANSYS Fluent. but we use a pressure-based solver for the non-restricted equations. That's relevant for the low velocity flow. Also, while using a KS non-realizable model for the turbulent flow. And we also use ANSYS symmetry, as you can see here on the right, in order to increase the mesh concentration. Our initial design, shown on the left, was simply purposed just to fit the chassis. It does include an aerodynamic device known as a splitter, which is used to divert flow. However, in summary, this was not able to meet the performance that we wanted. So after a few more iterations, we reached this point where we included an underbody and a rear diffuser. However, again, we did not reach the coefficients that we wanted. So after a few more iterations, we reached our final design, which did outperform last year's model by the following percentages: 14% and 15.3% minimization of the coefficients. And also, it's conducive to manufacturing. It's not a crazy design, however, it can still give us the performance that we were seeking.
So for the manufacturing of the body, we chose to use a vacuum-assisted RTM as a process. This is mostly due to low-cost materials and procedures. It had the ability to customize mold shape, give us a desirable fiber-to-resin ratio, as well as a good surface finish when using a female mold. We broke the design of the body into 4 molds, mainly, which we CNC'd out of foam and eventually stacked up all the layers, glued them together, filled the holes, and eventually used a gel coat for finish. Once that step was done, we added a wax layer for release, did the layup, and started the vacuum RTM. For the reinforcement of the composite, we used carbon fiber, approximately 3 layers across the entire body, and we used a 2x2 weave to obtain bidirectional properties, as well as a 2-part epoxy matrix that was donated to us. This here is the final product of the manufactured body. At this stage, we still need to finalize the mounting points, cut out the excess material, and do the final coating finish before competition. Even though I've shown this in a couple of slides, this is actually something that we've been working with the entire team that is for this year today, approximately for the past month and a half, and we put in roughly around 400 to 450 man-hours if you combine all of our efforts together. For the aerodynamic package, we also looked at a couple other things, specifically side pods, due to their benefits in terms of generating downforce and improving cooling. We started with a simple airfoil design and we progressed all the way up in here. But as of this stage, we haven't found the favorable coefficients of lift and drag, and as a result, we're putting priority on assembly of the entire vehicle first before we revisit this. If there is more time towards the end before competition, it is something that we would like to come back to, but as of now, we're sort of pulling the plug on that project. As a summary, we were able to develop a new body for the new chassis. We used ANSYS fluid for the analysis, and we were able to obtain favorable coefficients of lift and drag. We manufactured the body into 3 panels, which is currently waiting pending assembly, and we took a look at some aerodynamic accessories that we could incorporate, but as of right now, we haven't finalized any designs. The total cost of manufacture is roughly around $2,300, not including all of the labor hours that we put in, which of course would raise it up.
For the global and societal impact of this project, I'd like to remind you this is an international competition, so we are competing and idea sharing with teams from around the globe at the competition in May in Michigan. Apart from that, the standards and regulations that we followed and adhered to for the design and manufacture of our project are the same standards and regulations that teams from across the globe are adhering to. Here at FIU, we have a unique opportunity at the Engineering Gala. It's an event where the school invites approximately a couple of thousand students that are local to come check out the work that's going on. So we were able to do some of our testing outside, out in the parking lot, to show some of the students what we're working on. And also, here in this video, we have one of the Canadians team that came down and doing some testing. So that was a great opportunity to collaborate with them. And also, we work with we welcome the team from Venezuela to come and do some testing here as well. In conclusion, we were able to successfully redesign the cooling system. We were able to achieve weight savings, increase the cooling performance through the means of the model testing of the radiators and then moving on to the full-scale verification. We were also able to successfully redesign the body and manufacture it to fit the chassis as well as achieve favorable coefficient of lift and drag in comparison to the last year. And this project has served as a great opportunity for us as engineering students to bridge that gap between engineering students and working engineers, such that getting our hands dirty, working in the shop, and really work in multidisciplinary teams. As far as the future work goes, there's currently a Senior 1 design team that's working on the suspension, so they'll be integrating that into the vehicle. And the future work really for the team is to integrate the components that ourselves and our partnering senior design team are contributing to the team. I'd like to acknowledge our sponsors that have made this possible. We would not be here without them. And with that, I would like to conclude the presentation and open the floor to questions.
wires that you have in your system in any way?
Right now, this is on the engine stand, so this is just for testing. It's not how it's going to be in the vehicle. This engine stand is just so that we can work on our parts of the vehicle while the chassis is doing their part in parallel, so we don't obtrude in any of the work.
I'm saying for when you integrate it, like you should have a wire harness. Have you guys considered any sort of protection for your wires?
Yes, we do.
So I don't really have any details as to how we're going to protect them right now, but it is something that we typically do when we get ready for competition. So you could expect it to be done, yeah. If you'd like to ask more questions, we do have our chief engineer here in the back who would be happy to help you sort that out later.
Yeah, I just bring it up because it's something that always gets overlooked, and the majority of aircraft failures and of severe aircraft failures and the most of like aerospace failures are because like electronics are overlooked because it's not the cool part and it's not the like important part in like the overall scope. But if it breaks, then it kind of ruins everything else, and it would be really sad to see your car not cool the engine properly because your wire, you know, was burned through or melted.
Yeah, I would like to note that prior to even competing, prior to doing any of the dynamic events, we do have to go through a very rigorous technical inspection that adheres to all standards. So definitely if there's any issue or any safety problem with the wires, we would not be competing. So we definitely work to adhere to those rules.
There's one specific SAE guideline is 5, so we have to follow that for integration and pass tech before competition.
How many horsepower do you get out of that engine?
I think it's approximately 30 to 40. It's nothing big, but we're working with a very lightweight vehicle.
Can you hop it up, or you're limited?
Sorry, well, our biggest restriction is actually the intake of the throttle body. I believe it's 19 millimeters. So that severely limits anything else we could do because that limits how much air we can intake. So.
Can't put a turbo on it, or?
There are severe regulations for any type of accessories.
Oh, okay.
No nitrous on this.
Yeah, right.
Build it inside. Talk to me about the layup on this construction you built. Obviously it pulls down, which pulls that nose up, I assume, and then this section is going to go in the bottom. Is it all, because the bottom of the these chassis seems to not be flat. It seems to have angles, and there's no angles.
Yeah, so the mounting points that we're going to use, so we specifically or purposely made the bottom of the floor to be as flat as we could, so that we could try to benefit from some of the aerodynamic effects that occur on the ground. And we did that with in mind that it wouldn't connect with the chassis directly. So some of the mounting points that we're going to have to put together are going to have to make up for the space that we don't have here for that flat that you were pointing out. For the most part, though, you would have this section that goes underneath, and you see this layer here that's overlapping. We would have to get rid of the excess. This is supposed to be an axis cone, so that we can show the impact attenuator, and then also be able to do some work on the body. Does that answer your question? I don't know if you'd like to go into more detail.
That's fine, thank you.
I would like to add that with this body, of course, we do have some excess materials such as these flanges. And those are done purposely. This is how we are handing off to the team because as we approach competitions, you know, we don't want to have a perfect body now 5 months ahead of competition and possibly incur any type of damage to them. So as we move forward, they get painted and look really nice and all that. But at this point, the design is done by the manufacturer.
Did you guys have any issues when you were removing the carbon fiber from the mold?
Yes.
So I'm assuming you probably lost like a layer, or like you scuffed up the...
No, not at all.
No, so it came out fine?
Yeah, so the layup itself, the manufacturing was very good. What we had issues with was the gel coat. It didn't seem to cure properly, so when we tried pulling it off, it was sort of not creating necessarily a vacuum seal, but it was pulling a lot of force back. And so towards the end, one of the molds we ended up having to destroy to take out the piece. The top and bottom molds we were able to take out successfully, but the gel coat that was the finish on the mold was destroyed too. So if we were to reuse those molds, we'd have to redo the entire process. And I look into as to why was it didn't cure in the first place. We're not entirely sure what it is that happened, whether it was heat or we didn't have the right mixture for the gel coat finish.
And to add on to that, there were some things that weren't perfect, but of course, it looks rough, but I invite you to come feel it. It's very smooth surface.
It's not that it looks rough. The carbon fiber looks rough unless you like finish it up, which is fine. I was just curious because like the Ego team had issues, and the solution that we use is just add an extra layer, and if it breaks, and then you just keep on because it's sacrificial ply. And so I was just wondering if you guys encountered that, because that's pretty much the easiest solution if that was an issue. So.
Any more questions?